Hello, and welcome to this episode of Madison's Chemistry. Today we're going to be going over strong and weak acids and bases. The goal of this video is to understand the difference between strong and weak acids and bases and what will be major species present in solution, to also understand how to find the pH for all of these, and also to understand that even if something's a strong acid, that doesn't necessarily mean it's going to have a lower pH. So let's kind of delve deeper into all of this right now. Okay. So let's say here that we have a strong acid such as HBr, and it's going to go form H plus and Br minus. So we know that it's going to 100% dissociate because that's the definition of a strong acid. And it's not going to be in equilibrium. So if I was trying to find the pH, I would first make the relationship that our HBr concentration is going to be equal to our H plus concentration. So this is really important. And we'll be able to use this with all of our math in the future. Okay, so let's say that I knew that I had a molarity of 1 times 10 to the negative 2 of HBr. So that means that I know that 1 times 10 to the negative 2 equals our H plus concentration, because I'm just directly subbing it into this formula, which is my HBr concentration equals my H plus concentration. So if I know that my H plus concentration equals 1 times 10 to the negative 2, I'm able to find the pH by setting it equal to the negative log of H plus, and I will get that the pH equals 2. Okay? And if then I was asked to find the major species present in solution for HBr, it could either be HBr, Br minus, or H3O plus. We know if 100% dissociates, we shouldn't have any HBr, but we should have a lot of Br minus and a lot of H3O plus. So my graph would look something like this. Now let's say that we did the same thing but with a strong base. So here, the big equation that we're looking for is that my NaOH concentration is going to be equal to my OH minus concentration. And that's because it 100% dissociates, and that's how we're able to get this equation. Because if we start with some amount of NaOH, it's all going to go form OH minus. So now, if I was trying to find the pH of this solution, let's say that I knew that my NaOH concentration equals 1 times 10 to the negative third molarity. That means that 1 times the negative third molarity also equals my OH concentration. So if I were to take the negative log of my OH concentration, we'd get the POH. So that gives us a POH of 3. So now, if I wanted to find the pH, that equals 14 minus 3, which will equal 11. And if I was asked to find the major species present in solution, we could say it's either going to be NaOH, Na plus, or OH minus are the three things that could be in solution, right? We know if 100% dissociates, we won't have any NaOH, but we will have a lot of sodium and OH minus. But remember, this is the only thing that contributes to pH. Okay, so now let's keep going. Let's say that we have a weak acid. And let's say that we're working with HF. So we'd have H plus H2O, or HF plus H2O goes to form H3O plus F minus, right? So this is kind of from the equation that HA plus H2O goes to go form H3O plus A minus, right? This is the equation that we can use for all weak acids. This is our specific. This is all weak acid. Okay, so if I was trying to find, okay, so let's go backwards a little bit. First of all, it's not going to 100% dissociate. It's going to be an equilibrium. This equilibrium is given by our Ka expression. So we know that our Ka is going to be equal to products or reactants, so that'll be H3O plus times F minus over HF. Every acid will have a unique, every weak acid, unique Ka. And the lower the Ka, the higher the Ka, lower the pKa, higher Ka, stronger acid. So HF is a pretty strong weak acid. But anyways, if we were trying to now find the pH, we would need to know these two values, right? So these are in equilibrium, and we would solve for that. So if we wanted to solve for that, we'd have to have some sort of ice table, right? So HA plus H2O goes to H3O plus A minus. So let's say that we were starting with initial concentration of 1 molarity of HA. So we'd get 1 minus X plus X. Okay, so now we could take this value and, once plugging it into here to solve for X, we could take the negative log of that to find, at equilibrium, to find the pH of the solution. But it will have to be some sort of ice table to solve for these. So I know that can be kind of frustrating, but that's kind of the way that you got to solve it. And if, let's say that this question asked for what's the pH, we could say, what's the major species present in solution? So it could either be HF, F minus, or H3 plus, our three options. So it's actually going to be opposite of what we see with a strong acid. We're going to have a lot more of our initial reactants and then very little products because we're going to be favoring our reactants with this. Okay, so now let's keep going. Sorry. Okay, so let's do the same thing but with weak acids or weak bases. So let's say that we have the weak base ammonia. So it's NH3 plus H2O goes to go form NH4 plus OH minus. And so the general formula is B plus H2O goes to go form HB plus OH minus. This is our generic, applicable to everything. And so, okay, so now let's say that we were trying to find the pH. So first of all, we know it's not going to 100% dissociate. It's actually going to be favoring this side still. And we know that it's going to be in equilibrium, just like we saw with weak acids. So let's say we're trying to find that. So now instead of the Ka, we're going to have Kb. So we can say that Kb equals our products, which is NH4 plus times OH minus, all of our reactants, which is NH3, because we'll omit this. Okay, so a lot of times, just FYI, you're normally going to be given Ka. But if you want to solve for Kb, it's not very hard, because we know that our Kw equals Ka times Kb. And at 25 degrees Celsius, we know that our Kw equals 1 times 10 negative 14. So you can normally just play around with that to find what your Ka and Kb expressions would be. Okay, so if we're given our Kb and we set up our ice table just like we did up above, we'll not actually be solving for the H3O plus concentration, but we will be able to find this concentration. So we can do that negative log of the OH at equilibrium equals our POH. And we know that 14 minus POH equals pH. That's at 25 degrees Celsius. Okay, so that's kind of how you could find pH for every single one of the options, which would be strong acid, strong base, weak acid, weak base. So real quickly, I want to go over an example where we can see the difference to note that just because we have a strong acid doesn't necessarily mean it's going to be a lower pH. Okay, so let's say that we have HNO3 concentration equals 1 times 10 to the negative fifth. That means that our pH equals 5. Because remember, 100% of this is going to dissociate to form H3O+, because it's a strong acid. So now let's say we have the weak acid of HF again, and let's say that this concentration this time equals 1.0 molarity. Well, I don't exactly remember what the Ka is, but I'm guessing, let's just say that the pH is something like 3. Okay? So here we can see that it's actually greater than our strong acid, which has a pH of 5, and that's because this has a lower concentration. So if they're both at the same concentration, strong acid and weak acid are at the same concentration, then we know the pH of the strong acid is going to be smaller than the weak acid. But it has to be at the same concentration in order for us to make that conclusion. So I hope that makes sense, and I hope this video is useful. If you did find it useful, that would be awesome if you could subscribe. I will be posting videos every week on Gen Chem 2 topics. Thank you!